I'm at the Jet Propulsion Laboratory in Pasadena, and I'm here to see the first drone that's gonna fly on another planet. It's the Mars helicopter. Come on.
So, this is our baby.
No way.
Yeah.
That thing right there is the actual machine that is going to take off and land on Mars. It's going with the Mars 2020 mission. That is the Mars helicopter.
This will be the first powered flight in another planet.
I mean, this is that. Now, it's necessary to say first powered flight because in 1985, the Soviet Vega missions deployed 2 helium balloons on Venus. They transmitted data for over 46 hours while floating at an altitude of 54 kilometers in Venus's dense atmosphere, which at the surface has a pressure of over 90 Earth atmospheres. In contrast, Mars has very little atmosphere, only around 1% of Earth's.
Flying this kind of helicopter is equivalent to flying a similar helicopter on Earth at 100,000 feet. So you don't hear about many helicopters at 100,000. I think 40,000 feet is probably the record.
I checked. 40,000 feet is the record altitude reached by helicopters on Earth. 85,000 feet is the highest a plane has ever flown. On Mars, the air is even thinner than that.
Right, in terms of density is 1% of what you have in this room. So in this room, a cubic meter of air is about a kilogram.
Yeah.
The same cubic meter on Mars will be about 15 grams to 18 grams. So that
you have to push a lot of air down.
Yes, you gotta get a lot of air flowing. And so the obvious trick, if you will, is to spin the blades faster.
It can spin between 2,300 RPM and 2,900 RPM.
That is fast.
That is fast, yes.
2,300. Here I'm trying to work out exactly how fast that is. So I looked it up, and on Earth, helicopters typically spin their rotors at around 500 RPM. So the Mars helicopter will have to spin its blades 5 times faster.
But there are some limits. We really don't want to get the tips of the blades breaking the speed of sound.
Because then you have shockwaves and all
and you get all kinds of funky aerodynamics and transonic flows and things like that. So you don't want to go there. So we, in our designs, keep the tip mark numbers down to below about 0.7.
So 70% the speed of sound.
Yeah, so it's very conservative.
One advantage of flying on Mars is that gravity is only 38% of what it is on Earth. Even so, making the craft lightweight was essential.
Keeping the mass of this vehicle contained during the entire design process has been the major challenge.
Every single part had to be considered. The entire vehicle is less than 1.8 kilograms.
Whoa.
So less than 4 pounds.
That's about the same as this laptop.
The blades are foam core with carbon fiber layup. Each of them is about 35 grams.
Wow.
Yes, it's quite light, yes.
35 grams is the mass of 6 quarters. Think about that. 2 35-gram blades lifting an 1,800-gram helicopter by spinning 40 times per second in just 1% of Earth's atmosphere. How long can it fly for?
It's designed to fly up to 90 seconds.
A minute and a half of flight.
Yes.
To me, that sounds like forever. When you're talking about another planet flying autonomously by itself in 1/100th Earth's atmosphere, I mean, come on. That's a long time.
It is, yeah.
One of the questions I had was, why didn't they use a quadcopter design? Well, because on Mars, the blades have to be so long that the whole craft would barely fit on the rover. 2 counter-rotating propellers provide the simplest design. They also generate lift more efficiently when stacked on top of each other.
The bottom rotor sees the more compactified flow. The top one pulls it, the bottom one sees sort of a more concentrated flow. Right. So the bottom rotor actually can do better than if they were separated apart.
But how do you test a helicopter designed for conditions on Mars on Earth? What would happen if you just took your Mars helicopter and you tried to take off on Earth?
It would just make a lot of noise.
Really?
And it probably wouldn't get to full head speed either.
Because of how much atmosphere we've got.
Exactly. It's like trying to swim in a thick soup. We have a really amazing chamber here on lab called the 25-foot space simulator. And in that chamber, you could simulate any kind of atmosphere you want. You can go to Martian pressures, you could stay at Earth pressures, whatever you want. But that only took care of half of the problem. That was the aerodynamics aspect of it. There's the other part, which is the gravity. We needed a way to fake Mars gravity here on Earth, and the best way that we could figure out to do that was a gravity offload.
Gravity offload just means pulling up on the helicopter, so it only has to support about 38% of its weight, just like it will have to do on Mars.
And effectively, it was a high-tech fishing reel. So taking a brush DC motor, a reaction torque sensor, and a pulley, mounting that a couple stories in the air, and then attaching a fishing string to the top of the helicopter that would tug the necessary force required to offload the differences in gravity.
An actual fishing line?
Yeah, real fishing line.
But isn't that stretchy? Like, don't you want something that's perfectly rigid so as soon as you apply the torque, it gets applied to the craft?
Right. And we did a lot of testing with different vendors to find out which fishing line had the best spring constant for us.
What does the helicopter sound like? I imagined that in 1% of Earth's atmosphere, the helicopter would be pretty quiet.
Yeah, you're still at 1%, but it's still real loud.
Really?
Yeah, we have audio recordings of it too. But it's I would characterize it more like bah, something like that. When the gravity offload system was working and the chamber was pumped down, the helicopter thought it was on Mars. It felt like it was on Mars, the helicopter.
How do you actually steer this thing around and drive it?
So the way helicopters work is they have something called collective and cyclic. So what collectives do is they change the pitch on the blades uniformly. So throughout the entire revolution, if you move the collective, the blades will
change their
angle of attack, you'll get more lift. So that's basically what provides you heave control, right? You pitch more, you go up, pitch less, you come down. But then there's something called a cyclic on helicopters, which basically what it does is it modulates the pitch as it goes around. So it can pitch a little bit more here, less here. So it kind of like modulates. So what that does is it provides an asymmetric torque, right? When you're pitched up there, you get that additional torque. Now you get it, depending upon the stiffness of the system, you actually get it with that gyroscopic lag that can happen afterwards. So once you get an asymmetric torque, the vehicle wants to start pitching or rolling, right? So once it pitches and rolls, and you're doing it stably, you are now pointed in a direction, and your thrust vector now has a component that's horizontal in the direction that you pitched, right? So then you start translating in that direction.
I've heard that initially someone tried to fly it with a joystick?
Yes.
An early prototype?
If you were sitting right there on Mars and you were trying to joystick it, what is it like? And it's almost unflyable. And the reason for that, it's the aerodynamics of when you want to command a roll to the left, because you see yourself starting to move to the right, and you start commanding a roll to the left, there's a delay aspect. So that delay effect makes it very, very difficult for a human to try and pilot it.
You can't fly this from Earth.
Because of the 20-minute kind of time delay, so you have to really send sequences.
So essentially, you're going to push a button, and like 20 minutes later, it'll take off and do its thing, and then you'll find out.
The way this flies autonomously, it has onboard gyros, onboard accelerometers, and onboard camera, and altimeter, and an inclinometer. And so using that sensor suite, real-time measurement, against the terrain, and of course the gyros and the accelerometers sensing on board, the real-time estimation of the state of the vehicle is made continuously, again, hundreds of hertz. And then that's fed into the closed-loop control algorithm that takes the estimated state and then generates the correction that's needed at the blade level, and then the blades are continuously being controlled. So when you see video tapes of our successful flights, right, and the vehicle looks dead calm, is coming up and hovering and going laterally, coming back, the machines are working very, very fast and very, very hard. It just looks very calm, but yeah, so the blades are being continuously controlled.
That is amazing.
Yeah.
How will it handle a gentle breeze?
A lot of the movies depict
Dust storms?
the big dust storms.
Welcome to NASA's Jet Propulsion Laboratory in Southern California. We are gearing up for NASA's Perseverance rover to touch down on Mars. Happening in an hour and a half from now, the rover will attempt to land in Jezreel crater. It is the most difficult landing site on Mars ever attempted. Thank you for joining us. I'm your host, Raquel Villanueva. In the past, mission team members gathered in our mission control for landings. But this time around, we have COVID safety measures in place. Today's landing will look a little different than what you've seen before. I am in a room by myself, and so is my co-host. Here in the Spaceflight Operations Facility, team members are in different parts of this building. Some are in mission control, others are upstairs for landing operations. We also have isolated rooms for our guests on this show. In total, we have 8 locations covered by 14 robotic cameras that you will be seeing. One of those locations is the dark room, the heart of NASA's Deep Space Network. Think of it as a giant communication switchboard. This is where spacecraft phone home to us from across the solar system and interstellar space. The Deep Space Network has been tracking Perseverance since it left Earth. And there are lots of ways you can watch landing today. We have a 360-degree camera inside the control room. It lets you experience the landing right along with the team while seeing this broadcast. We also have the clean feed. It shows an uninterrupted view of mission control and audio. También tenemos un programa en español. To tell us about it is host Diana Trujillo, who also works on the mission.
Thank you, Raquel. We're so excited to be the sister live broadcast in Spanish. Sintonízate nuestro programa en las redes sociales de Twitter, YouTube y Facebook en la NASA en español para que nos acompañes a un tour virtual de la NASA con entrevistas con astronautas, con participación de artistas, con entrevistas con científicos e ingenieros de Perseverance, con Plaza Sésamo y mucho más. ¡Te esperamos!
Gracias, Diana. And don't forget, we want to see how you are watching the landing today. Use the hashtag Countdown to Mars to send us your photos and videos. To preview what interviews are coming up is my co-host from the JPL News office, Marina Jurica.
Thanks so much, Raquel. The excitement is building behind me right here in Mission Control as we count down to the Perseverance landing. We will be talking to some of the many people who made today possible, from scientists to engineers on the Mars 2020 Perseverance rover team to folks from NASA headquarters giving us a look into the future of Mars exploration. A little later, we will also be speaking with the students who named the rover and the helicopter. Inspirational stories as we prepare for another landing on the red planet. Back to you, Raquel.
Thanks, Marina. Let's give a shout out to the students around the nation learning about Perseverance's mission to Mars with their teachers. We're happy you're with us on this exciting day. Later in the show, we will be answering some of the questions you submitted through your classrooms. Landing on Mars is complex. The team will be calling out milestones as they happen. It's fast-paced, and you'll hear lots of technical terms. To help us translate and explain what is going on in mission control is Swati Mohan. She is part of Perseverance's landing team. Thanks for guiding us through landing today, Swati.
Hi, Raquel. I'm happy to be here today.
So, Swati, what is the status of the Perseverance rover right now?
So Perseverance is still in space right now, about 9,000 miles from Mars. So far, she is healthy and on course.
And it takes time to send signals between Earth and Mars. Can you let us know how that affects the information you are seeing?
So Mars is about 127 million miles from Earth right now. That means it takes about 11 minutes from light to travel from Mars to Earth. So all the information that we receive from Perseverance actually happened 11 minutes ago. So the round trip is 22 minutes for us to send a command to Perseverance and hear back on the ground that she's received that command. This is what we call two-way light time.
That's good to know. And can you tell us who else is in the room with you right now?
The operations team is split into 2 different areas. Here in the cruise mission support area, we have primarily the team that has been flying Perseverance from Earth to Mars. You'll see the placards with the roles of each of the people by their stations. Some of the people you may hear talking today are the flight director, who is the conductor of our operations orchestra here, the entry, descent, and landing activity lead, who is a member of the landing team tasked with understanding the execution of entry, descent, and landing, and then also the telecommunications and entry, descent, and landing communications engineers who will be monitoring the signal from Perseverance through the different paths that we have. Upstairs, in what we call the war room, we have almost the entire entry, descent, and landing operations team. And then across the hall from them, we have the surface mission control room, where the surface operations team is ready and waiting to take over as soon as Perseverance's wheels touch the ground.
And you have been part of this mission for years now. Can you tell us what have you been working on?
I've been working on Perseverance for almost 8 years now as a guidance, navigation, and control engineer, working primarily on entry, descent, and landing. One of my big tasks was to help with terrain relative navigation. Perseverance will be the first mission to fly terrain relative navigation. So while she's descending on the parachute, she'll actually be looking at the ground with a camera, seeing where she is with respect to the Martian surface, and choosing a safe spot to land that she can get to. After so many years of working on the mission, it's an honor to be here today as the mission commentator.
We're happy to have you here. Thanks, Swati. We'll be checking back in with you in just a few minutes as Perseverance approaches its next milestone.
Sounds good.
But for now, let's learn more about the rover's mission once it lands on Mars.
You know, Mars is the closest place that we can reach with robotic exploration that we think had a really good chance of having ancient life.
The Perseverance rover will land at a location called Jezreel Crater. Jezreel Crater is a very interesting place. It's a crater that once held a lake.
There are a lot of craters on the surface of Mars that could have once hosted ancient lakes, but not every crater that we think had a lake actually preserves evidence that that lake was there.
It had an inflow channel and it had an outflow channel. That means it was filled. The crater was filled with water.
In Jezreel, we have probably one of the most beautifully preserved delta deposits on Mars in that crater.
This is a wonderful place to live for microorganisms, and it is also a wonderful place for those microorganisms to be preserved so that we can find them now so many billions of years later.
There is no other place on Mars that has the unique combination of a lake setting, a beautifully preserved delta, and the diverse mineralogy that we have in Jezreel Crater. So it's truly a special landing site.
The major goal of the Perseverance mission is to investigate astrobiology on Mars, and in particular, to address the question of whether life ever existed on Mars. The Perseverance rover starts with a design that's very similar to Curiosity. We've added to it a whole new set of science instruments, and these science instruments were purposefully selected to help us in the search for biosignatures.
We're going to be taking microphones with us. For the first time, we're going to have that human sense on another planet.
Perseverance carries with her a grand experiment in spacefaring technology, a helicopter, the name of which is now Ingenuity.
One of the major upgrades that Perseverance has from Curiosity is that it's able to self-drive for a distance of up to 200 meters per day. As the rover is driving, it's literally building the map of the road it's driving on Mars.
Scientists for years have told us that to really unlock the secrets of Mars, we have to bring samples from Mars back to Earth.
So what Mars 2020 is going to do is to drill samples, put them in small tubes. We're going to seal it in its own individual tube. We set them on the surface to provide a target for the second two missions, which hopefully will get in development in the next several years and could potentially get the samples back to Earth by 2031.
Perseverance is a very, very profound first step in both our understanding of our place in the universe and a stepping stone towards human exploration on Mars.
You are watching live Mars landing commentary, and Perseverance is about to reach another important milestone. Swati, can you tell us what is happening?
We are at a milestone where the operations team determines whether they're ready to turn off the transmitter to Perseverance. Turning off the transmitter is like taking your hands off of the wheel. At this point forward, Perseverance would be on her own to execute entry, descent, and landing over 500,000 lines of code. Let's listen in.
Okay, all stations, we are ready for the transmitter off.
Astrobiologist collecting samples that we will bring back to Earth. And for us, of course, those are where the best laboratories are of all of humanity. Some of them still remain to be explored by some that are not yet in the science community yet. And that's what we're looking forward to. It's that new phase. The other element that I want to talk about is the amazing technologies that are there. And of course, one of my favorites is the Ingenuity helicopter, this in search of this extraterrestrial Wright brothers moment, you know, controlled flight for the first time elsewhere, Raquel.
Great. And we have a student question on video for you from Macy.
Hi, my name is Macy Ragsdale. My question is anything alive on Mars? Thank you.
Well, Macy, I'm so glad for your question. It's a question I ask myself. Is anything alive there? And frankly, at the surface where we're going right now with Perseverance, we do not believe there's anything alive right there because of the radiation that's there. It's chilling, cold, and there's really no water there. But guess what? We think that 3 billion years ago, this looked like a stream that you may see on Earth. And frankly, a lot more similar than Earth, with water with a magnetic field, just like the Earth with an atmosphere. And the question is, at that time, 3 billion years ago, were there single-cell organisms, just of the type that developed on Earth? So is there life on Mars overall? We don't know, but where we're going right now, we're really looking for ancient life, and that's what we're so excited about.
Thank you for your time today, Thomas. And thanks to everyone who has been using the hashtag Countdown to Mars. Here are some of the photos that you've sent in so far. Let's take a look. Now, please keep sharing with us how you are watching this moment today. For now, let's go back to Swati for an important update to what's going on in mission control as we get closer to another milestone.
Hi, Raquel. This next milestone is a communications pole. So during landing, not only will Perseverance talk directly to Earth, but we'll also be talking to 2 spacecraft that are currently orbiting Mars, the Mars Reconnaissance Orbiter and the MAVEN spacecraft. This poll is to confirm with the Mars Reconnaissance Orbiter spacecraft and the MAVEN spacecraft teams that they are ready and on track to support the relay from Perseverance. Let's listen in. Oh, Maggie.
EDL comm flight.
Go flight.
Have you performed the comm check and readiness of the orbiters?
We have performed the voice check and the readiness poll and can confirm that MRO, MAVEN, EDA, Radio Science 1 and 2, UHF, DTE, DSN, and EDL GDS are all ready to support.
Copy, EDL comm.
So we've just heard that we have confirmation from each of the different orbiters and all of their support equipment on the ground that they are ready and are on track to support the relay from Perseverance.
Great, thank you, Swati. And we just heard that communications readiness poll, which means we are ready to relay the data Perseverance will send to get a better idea of what the rover looks like as it approaches Mars. We have a NASA program called EYES. The visualization lets anyone watching track Perseverance. Here's how the program works.
Follow Perseverance on its journey to the surface of the red planet with eyes on the solar system. From your desktop or mobile device, go to eyes.nasa.gov. Click on the banner, and now you're with Perseverance in real time through every step of EDL, entry, descent, and landing. This interactive experience lets you ride along from whatever perspective you choose. Click and drag, scroll in, scroll out. Check out the descriptions and explanations to increase your EDL expertise. Experience every entry, descent, and landing event precisely designed and executed to land Perseverance safely on Mars. The EYES experience is based on predictive data, but during this broadcast, you'll see a different visualization called Ranger, and it's based on the real communication the team in Mission Control receives from Perseverance in near real time. This is the visualization the team will follow as data fills their screens while monitoring the health of Perseverance on its nerve-wracking course to another successful Mars landing. Enjoy the ride.
You are watching live Mars landing commentary. Stepping outside Mission Control to talk to us is Perseverance system engineer Matt Smith. Thanks for joining us today, Matt.
Hey, Raquel.
Well, coming from Mission Control, we are going to hear terms related to landing. Can you help us understand what some of them mean?
Sure, definitely. One thing you'll hear a lot about is telemetry. So telemetry is just our way of talking about data that's coming from the spacecraft and telling us important things like temperatures on the vehicle, pressure, how much fuel we have left, and other things that we need to understand for the health and safety of the vehicle. You'll also hear the word nominal, hopefully. Nominal means everything is expected, everything is okay, we're good to go. You'll hear also a lot about velocity and deceleration. So velocity is just our speed combined with the direction we're going. And deceleration is our slowing velocity. So we're coming in at over 12,000 miles per hour, and we're going to slow down to a nice, comfortable 2 miles per hour at landing, and that's our deceleration. Speaking of landing, you may hear a couple important terms at landing itself. One is RIMU stable. So the RIMU is a device on the rover that measures the rover's orientation and whether it's moving. So we want a nice, stable landing spot without any motion. You'll also hear UHF stable, hopefully. UHF stable refers to good telecommunications link with the rover and indicates that we've had a good separation between the descent stage and the rover after the sky crane maneuver. Finally, you may also hear Tango Delta nominal or touchdown nominal. That means we've touched down on the surface of Mars within the expected range of safe landing speeds.
Thanks for that breakdown. Now, this is your first Mars mission. What have you learned from this experience?
Yeah, one of my takeaways is that you can almost never be too careful when it comes to Mars. You definitely can't take Mars for granted. You know, we've checked and double-checked and triple-checked everything on our way to Mars. And, you know, even though we've done this once before using the sky crane technique on the Curiosity rover, you know, I think everyone's going to have everyone's going to hold their breath until we're on the surface of Mars this time around.
And we have a social media question coming in. Nor the Door on Instagram asks, how complicated is the automated landing sequence and who wrote the code?
Yeah, it's quite complicated. The automated landing software needs to do literally hundreds of things all on its own, just right with sub-second timing accuracy. And it's the result of many hundreds of people over many years, stretching all the way back to Curiosity and then improved for the Perseverance landing today at Jezreel crater.
Great. Thanks for your time today, Matt, and good luck.
Thanks.
Now, landing on Mars is hard. Landing on Mars during a pandemic is even harder. The team behind the Perseverance rover faced one of its biggest challenges when the coronavirus pandemic struck. Here's how they kept the mission going.
When the pandemic struck, the future was certainly unknown. It was like walking into a blind, dark alley. You didn't know what was there, what was in front of you, what you were going to have to deal with.
It's something that nobody expected. It's something that nobody could plan for.
So we all were asked to start working from home.
Rather than your first priority being mission success and getting to the launch pad, your first priority immediately gets displaced, and it's now the safety of the people.
And it took a lot of work to put stuff together in order to keep momentum going, to keep people working safely, keep them healthy, and to keep the project on schedule.
We called the effort Mars 2020 Safe at Work, and the objective was to keep the team as safe or safer than they would be if they were not working. You know, putting a spacecraft together that's going to Mars and not making a mistake, it's hard no matter what. Trying to do it during the middle of a pandemic, it's a lot harder.
And liftoff. As the countdown to Mars continues, the perseverance of humanity launching the next generation of robotic explorers to the Red Planet.
Certainly never done something like this before. Try to lead a team that's flying a spacecraft on the way to Mars while getting ready for landing, while doing it all from home.
There's no doubt that working in isolation, not virtual isolation, but in physical isolation from everyone else, is a challenge.
We had to rethink and redesign what it meant to operate a spacecraft in flight when we couldn't all be in the same room in mission control, seeing the data come down from Perseverance.
It was a major change going to that, looking at everyone on a screen instead of in person.
Because of the pandemic, you can't, just pop over your cubicle wall and talk to the person next to you.
It's definitely been a challenge to figure out how to communicate and get everything done remotely, but we've managed to make it work.
We are explorers. Our job is to go into the unknown, and this is just another example of the unknown.
We're really doing something that's transformative and trying to understand whether or not life evolved on another planet. That's the fundamental objective of this mission.
We're all still connected by this incredible mission and this wonderful team that we have the opportunity to be a part of. So that keeps at least me going.
Pretty much everybody that I've talked to that's associated with the mission has said the same thing, which is you could not have come up with a better name than Perseverance.
It's an amazing serendipity that we get to persevere through working on Perseverance.
Joining us now is Perseverance Deputy Project Manager Matt Wallace. Matt, just how ambitious is this mission, and how does this team stay on track with unexpected challenges like the pandemic?
Well, it's a very ambitious mission. We're carrying not only a host of new, extremely capable science instruments to do that science mission that we've talked about, but also a number of technology experiments that provide feed-forward information into the next set of robotic explorers or even human exploration of Mars. So there's a lot for us to do. We look a lot like Curiosity, but in fact we're carrying 50% more payload down to the surface of Mars, and so it's been a big challenge. And it was particularly challenging when the pandemic struck. It came at a critical time in our processing. We were just months away from launching. We're trying to essentially get the spacecraft assembled, do the final tests. We did not have a lot of margin in our schedule, and our focus just entirely shifted from that to keeping the team safe and keeping their families safe. And we had to do that quickly, to make the adjustment quickly. I think, we got through it with a lot of help. A lot of people stepped up to make it happen. The team was tenacious, and we managed to get it launched and fly it to Mars. Thanks to a lot of help.
And Matt, just how large is the team that worked on Perseverance?
It's a big team. A couple thousand people here just at JPL, in fact, have worked on the mission. And then almost every other NASA center has contributed in some significant and critical way as well. We have over 1,000 industry partners that have provided hardware into this mission from 44 different states, 60 different cities, and of course we have international contributions from Europe and many other international providers as well. So it's a big team. It's taken a lot of people to get us to where we're at.
That is a big team. This is the most difficult landing site ever attempted. Now, why do you think Perseverance is ready to land in Jezreel crater now?
Jezreel is tough. I mean, it's scientifically fascinating because it's got a lot of things like craters and rock fields and cliffs and sand dunes and that sort of thing, which are great for the science community. That's exactly the type of features they're looking for to learn more about Mars. But they're all landing hazards for us. And so we've had to add new technology to relevant navigation, which is the ability essentially to divert away from hazards. But we have taken this system through the same types of paces that we have in previous missions. We've used the same techniques, the same best practices for engineering verification, and in many cases we've used the same people. This, in fact, is my fifth Mars rover mission, and I'm not alone. There's other people on the project in the same situation. So, the team has given it everything they've gotten to put it all out there and to make this successful, and I think we're ready.
Thanks, Matt, and good luck on your 5th mission.
Thank you very much.
Well, Jezreel crater is a location on Mars that has intrigued scientists for years. Let's head over to Marina to learn more about the science goals of the mission.
That's right, Raquel. Here to explain why we want to go there is Deputy Project Scientist Katie Stack Morgan. Welcome, Katie.
Thanks, Marina. Glad to be here.
Now, Perseverance is landing on Mars at the Jezreel crater. Why is it that you and the team chose this particular area?
Yeah, so scientists believe the Jezreel crater is one of the best places on Mars and possibly the entire solar system to look for signs of ancient life. Jezreel contained an ancient lake and has within it one of the best preserved ancient delta deposits on the surface of Mars. And deltas form when a river enters a relatively open body of water, like an impact crater, and deposits the sediment that it's carrying into the lake. And we know based on studies of deltas and lakes here on Earth that they're great places to concentrate and preserve organics and support microbial life. We're also excited because Jezreel exposes rocks that are between 3.5 to more than 4 billion years old and represent a variety of different geological processes.
Now, this might be a tough choice, but what do you think would be the most rewarding scientific discovery that we expect to get from this mission?
Yes, hands down, I think the most rewarding discovery I think we can make with Perseverance would be finding a truly compelling ancient biosignature on Mars. The rocks in and around Jezreel crater record a period of time when life first arose in the solar system, and we have the opportunity with Perseverance to study the evolution of the planet from a once habitable world likely capable of supporting ancient life to the cold, barren planet we know Mars is today.
And why do you think, Katie, it's so important to find out if there really is or was ancient life on Mars?
Well, the question of whether there's life beyond Earth is one of the most fundamental and essential questions we can ask. And our ability to ask this question and develop the scientific investigations and technology to answer it is one of the things that make us as a species so unique. And based on everything we know about Mars in the past, it absolutely should have been capable of supporting ancient life. So we can find out an answer to the question, where there were habitable environments, was there life? And studying the possible emergence of life on ancient Mars can also help us better understand the conditions that led to life on our own planet.
That's so fascinating, Katie. Now we're going to take a question from a student, Vara.
Hi, I'm Vara, and my question is, why was Mars able to sustain lakes and rivers ages ago, but cannot now? Isn't it cold enough to make water, and isn't it always? Thank you.
Yeah, that is such a great question. And one of the things that protects our atmosphere here on Earth and allows liquid water to be stable on our own planet is the fact that we have a magnetic field protecting that atmosphere. We think that Mars lost its magnetic field way back billions of years ago and left the atmosphere exposed to things like solar winds and cosmic rays that basically blew that atmosphere away. And once that happened, liquid water wasn't stable on the surface of Mars anymore. It was too cold and the pressure was too low. And so now Mars is not capable of supporting liquid water and likely not capable of supporting life at its surface.
Well, thank you so much to Vara for that great question, and a big shout out to all the kids that are watching out there today. And thank you so much to you, Katie, for joining us. That was so great.
Thank you.
Now sending it back over to you, Raquel.
Thanks, Marina. Earlier, we were able to catch up with the communication systems engineer, Chloe Sakier. She helps us break down the system used to track Perseverance during landing.
The communications infrastructure supporting Perseverance's landing is quite complex. We've rallied a truly global network of relay and communications assets to help us capture and record those precious minutes of entry, descent, and landing, or EDL. We receive a stream of engineering telemetry via these communication assets that helps us see and understand exactly what's happening. Perseverance sends direct-to-Earth X-band tones, each of which provides us with indications of critical entry, descent, and landing events. During entry, descent, and landing, we have 2 Mars orbiters listening for the ultra-high frequency, or UHF, signals from Perseverance. These orbiters relay these signals to deep space network stations on Earth, Madrid in Spain, and Goldstone in California. The Mars Reconnaissance Orbiter, or MRO, has reconfigured its software to perform a type of relay called bent pipe. This will provide us with near real-time telemetry during entry, descent, and landing. We have coverage from the Mars Reconnaissance Orbiter from just before entry to a few minutes after landing. The telemetry we receive will be delayed by the time it takes light to travel from Mars to us back on Earth. Additionally, the Mars Atmosphere and Volatile Evolution spacecraft, or MAVEN, is recording these UHF signals and will be relaying that recording hours after landing. MAVEN will be covering us from around the time of cruise stage separation until a few minutes after landing. We also receive what we call heartbeat tones, which are indications that the spacecraft is alive and progressing throughout entry, descent, and landing. It's important to note that while unexpected, we could lose our communication links and still land safely. Because Perseverance is doing entry, descent, and landing completely autonomously, she doesn't need our help to joystick the landing. The communication links give us added visibility.
And you can see Chloe hard at work inside Mission Control right now. Perseverance's landing might look like the system the Curiosity rover used back in 2012. But landing on Mars is difficult. There's always a risk involved. Here's what needs to happen for Perseverance to touch down safely in Jezreel Crater.
Nothing can be taken for granted when you get to Mars. There's a lot of things we just don't know.
Space always has a way of throwing us curveballs and surprising us.
I mean, until we get the data that says we're on the ground safely, I'm going to be worried that we're not going to make it.
Entry, descent, and landing is often referred to as the 7 minutes of terror because it takes about 7 minutes to get from the top of the atmosphere of Mars to the ground safely.
The spacecraft has to do all of this by itself.
There are many things that have to go right to get Perseverance onto the ground safely.
There's a lot counting on this. This is the first leg of our sample return relay race. There's a lot of work on the line.
Starting about 10 minutes before atmospheric entry, we get rid of really the spacecraft part of the rover that's been supporting us.
We come screaming in to the Martian atmosphere at 12 to 13,000 miles per hour.
And the heat shield is what dissipates all that initial energy through friction.
The vehicle will continue actually flying itself through the atmosphere. It's sort of like a transforming vehicle that went from a spacecraft, and now it's kind of like an aircraft actively guiding itself.
When we're going slow enough, we deploy a parachute.
It's the biggest supersonic parachute we've ever sent to another planet. It's critical for slowing down the vehicle.
Perseverance's entry, descent, and landing borrows heavily from that of Curiosity.
But fundamentally, Perseverance is a different rover. She's bigger, she has different instruments.
We've added a lot of smarts on the inside to make it more capable so that it can deal with the landing site that we've given it.
The science team identified Jezreel Crater as basically an ancient lake bed and one of the most promising places to look for evidence of ancient microbial life and to collect samples for future return to Earth. The problem is it's a much more hazardous place to land.
When you look at Jezreel, all you see is danger. How do we go to a site that we never thought was safe enough to go to before? So the heat shield, which has protected us all the way through entry, is no longer necessary. We need to get that off so that we can actually see the ground. And we can see the ground in a couple different ways.
Perseverance will be the first mission to use terrain relative navigation. So while it's descending on the parachute, it will actually be taking images of the surface of Mars and determining where to go based on what it sees. This is finally like landing with your eyes open. Having this new technology really allows Perseverance to land in much more challenging terrain than Curiosity or any previous Mars mission could. Amongst the rocks and the craters and the cliffs, these things are hazardous to the rover, but these are the things that are interesting to the scientists.
Once Perseverance has figured out where she is, we jettison the back shell and parachute and light up our rockets. Those rockets help us steer to a safe landing spot that's nearby.
That descent stage takes us all the way down to about 20 meters off the ground.
That's when we start the sky maneuver. And once the rover has hit the ground, the descent stage will cut loose from the rover and fly away to a safe distance. Surviving that 7 minutes is really just the beginning for Perseverance. Its job, right, being the first leg of sample return to go look for those signs of past life on Mars, all that can't start until we get Perseverance safely to the ground. And then that's when the real mission begins.
With us now is Al Chen. He is Perseverance's entry, descent, and landing lead. Al, you were part of the Curiosity rover landing. Does it get any easier the second time around?
It absolutely does not, especially when considering we're trying to land the biggest, heaviest, and most complex rover we've ever built at the most dangerous landing site we've ever attempted. Jezreel may look great and promising from a science perspective, but it's absolutely treacherous for landing. There's a cliff wall that's about 200 feet tall that runs right through the middle of the landing site. There are craters full of sand that even if we landed them, we would not be able to drive out of. And there are rocks to the east and actually all over the place, rock fields. That would be a bad day for us if we were to land on them.
Now, Al, what new technology makes this type of dangerous landing possible?
Perseverance is carrying two new technologies that are really kind of under the hood smarts that are allowing us to land at this kind of treacherous landing site. The first is range trigger. That's the ability, we've given Perseverance the ability to decide for herself, based on where she is, when to deploy the parachute. Previously, we used to deploy parachutes, that supersonic parachute, based just on navigated velocity. But now Perseverance has the smarts to figure out where she is and deploy that parachute at just the right place to make sure that we shrink where we could come down. That actually reduces the area, that error ellipse, where we can come down on the ground, from something that was on the order of 15 miles long by 12 miles wide for Curiosity to about 5 miles long by 4 miles wide for Perseverance. So that's quite a bit of reduction. Second, the next piece of technology that's helping us land there is terrain relative navigation. In the past, after we've popped off the heat shield, we've taken pictures of the ground as it's been coming up, but we haven't really done anything with them. This time, Perseverance is carrying a camera to take pictures, but also a kind of second brain to help it figure out what those pictures are telling it and match it up with an onboard map from a satellite. That allows it to figure out exactly where she is. Suddenly then, she can then fly to safe spots that are nearby once she really knows where she is. It allows the site to not have to be as flat and boring as a pancake as some of our past sites have been, the entire area we could come down. Now we just need little pieces of that site to be small enough and safe enough for us to land in safely and fly there after we've gotten rid of the parachute.
And we also have a social media question coming in. Sansakari14 on Instagram is asking, how does the sky crane decide where to move itself after the payload lands?
After the payload lands, after the rover touches down, the sky crane, the descent stage, which is that rocket-powered jetpack above it, the first job, of course, is to make sure you don't hurt the rover. So it'll turn forward or backward so that the engine plumes don't pass over the rover. So it'll come up and start to turn. And it'll go in whichever direction is closest to north. So it can either go forward, if that's the way north is, or go toward the rear of the rover, if that's where north is. And it'll fly about 1/3 of a mile or so away.
Thanks for talking to us today, Al.
Thank you very much.
Now, let's head back to Mission Control for an update from Swati.
Hi, Raquel. So remember that command that we sent at around 11:35 to turn the transmitter off? We are just about to get confirmation that Perseverance has received the command. The command took 11 minutes to go to Perseverance, and then the reply took 11 minutes to get back from Perseverance to the ground. So we should hear any second now that we have officially turned off the transmitter. And after that, we will be about 4 minutes from the start of entry, descent, and landing mode. At this point, we will transition from the cruise approach mode to entry, descent, and landing. And that means our travel from Earth to Mars is done, and now we just need to get to the surface. So far, things are looking good.
Greetings, greetings. Bill Nye here, CEO of the Planetary Society. Excited indeed for another landing on Mars. Everybody, this is just an amazing achievement. I know you hear people talking about it, but it is really a difficult thing. To go to Mars, you can only go every 26 months. The Earth has to catch up with Mars. You got to go from 5 kilometers a second with the 10,000 miles an hour, 15,000 kilometers an hour, down to 0 in 7 minutes. It ain't so easy. And so here to join us for the landing party, as we like to call it, are just some fantastic people, everybody. I want to thank the members of the Planetary Society, 50,000 of you, us around the world, who just think that the exploration of space is worthy use of our intellect and treasure. So I am honored to introduce a few people. First, I would call it camera right, but it might look different for you, is Raquel Nuno. She there she's waving. She's the Space Geologist on Instagram. You can follow her. And she, just to throw out some acronyms, she's getting her PhD at UCLA in planetary science. And Raquel, you worked a little bit on the ground, or testing the ground penetrating radar for this mission, right?
Yeah, we were, I helped look at the sites that we would actually test the ground penetrating radar that is on the rover right now going to Mars. And I'm so excited to have been a part of that.
It is just cool as heck. So next over is someone you know very well. By that, I mean, Raquel, you know pretty well, is Derek Muller, who, as you know, is the guy who does Veritasium on the electric internet. What do you got? 8 million followers. And you, Derek, you went and watched the testing of the crazy helicopter.
I did. I was so lucky to get there on like the last day when they were putting the cover on, so I could just like see inside it. And I didn't get to go in the clean room, but I was literally meters away from the helicopter. So that was awesome. I also went to the launch of the actual rocket 6 months ago. So it's just phenomenal to think that payload that was in that rocket that I watched shoot up into the sky is just about to hit its target. It feels very surreal.
It's amazing. If you've never been to a launch, everybody, they're just amazing. The ground shakes, your clothing shakes, your hair shakes. The thing is so powerful because it's such a long way to Mars. And just imagine, you guys, we're sending a helicopter to another planet to get the view that, for those of you who've had flying dreams, to get such a thing for real. It's really just an amazing undertaking because the Martian atmosphere is crazy thin, 0.7% the atmospheric pressure of Earth. So the blades on this helicopter have to spin crazy fast, and then steering the whole thing is non-trivial. All right, cool. And Raquel and Derek, you'll be giving us some color commentary. But on top of that, people, the president of the Planetary Society, a member of the Perseverance Mars rover team, one of the people that helped pick the landing site for this mission, is Dr. Bethany Ehlmann. She's a professor at Caltech, along with being part of the science team. Bethany, this is a very, very exciting day for you. How long have you been working on this? 8 years?
Yeah, it's an incredible day, Bill. It's been about 8 years since first part of the teams that proposed instruments to this rover.
So everybody, we have a lot of problems here on Earth right now. First to admit, we got a pandemic. If you're in the US, we got this crazy apparent mismanagement of our electrical system. All right, we have people suffering in all sorts of ways. We have a lot of problems to solve. But this kind of mission still brings out the best in us. And it is working. It is part of this huge human endeavor to find out, to seek answers to two questions that, for me, was best articulated by one of the founders of the Planetary Society, Bruce Murray, who was the head of this very same Jet Propulsion Lab during the disco era, as I like to say, when Voyager and Viking landed on Mars, Viking 1 and 2, and Voyager 1 and 2 left the solar system. Bruce Murray used to say, there's two questions that get to us all. Are we alone in the cosmos? And where did we come from? Put another way, what are humans doing here? So I'll just say again, if we are able to find evidence of life on Mars with this mission or this sequence of missions that Perseverance is part of, it will change the course of human history. It will be profound. Everyone will feel differently about being a living thing in the cosmos if we can find evidence of life. So the instruments that Dr. Ehlmann and her people, colleagues, worked on are put there to look, to seek something that might be a fossilized bacterium or fossilized Martian microbe, a Mars probe, as I like to call it. And everybody, it would be a discovery as profound as Copernicus. The planets go around the sun, not the sun around the planets. Or Galileo, hey man, or colleagues, I looked at this dot in the sky and it turns out it seems to have moons orbiting it or something going around it. Oh, these are individuals who made these remarkable discoveries, but this discovery, if we are able to make, or all the discoveries we'll make, will not have been made by a person, will be made by a team, by a society who invested its intellect and treasure. And I'm in the US, this mission is from Jet Propulsion Lab in the US, but it's an international mission. There are scientists from all over the world working on this, and the instruments were built by people all over the world. It really is a remarkable day. Whew. Thanks for tuning in. Over to you, Bethany.
Well, you set me up. Yeah, it's really an incredible day. And for those of us on the science team, it's a mixture of just excitement, nervousness, anticipation. As I said, many of us have been working toward this for seven or 8 years. There's an enormous effort to select the landing site, enormous effort to build the instruments, calibrate them, build the rover, get it all integrated, get it to Cape Canaveral. And that was done during the pandemic. This was a heavy lift. This was Perseverance. And we are very much looking forward to getting Perseverance on the surface to start the exploration.
So, it's got a piece of plutonium in it, and it will run for years if we can get it on the surface. And everybody, another thing I'm really excited about, as soon as it lands, you may have heard people talking on the NASA feed, which for me would be camera right. I don't know where yours is, but about the bent pipe. So, Bethany, what is the bent pipe?
Yeah, so some of you who are following the NASA TV feed might have heard about bent pipe relay of the data to Earth of this landing event. Okay, so it requires some background. There are basically 3 ways data can get to Earth. First, the rover can send it directly to Earth from its antennas. But see, the problem is during the last 2 minutes of this landing, Earth has set in the sky. It's no longer up, so the rover can't communicate directly to Earth any longer. So then you have a few choices. You could do what is typically done with rover data, which is called store and forward. And that means the rover sends the data, and after some time, the orbiter sends it back to Earth. But that wouldn't be very exciting. We would all be sitting here waiting in anticipation for hours as to what's going on. So that is why NASA is doing what's called bent pipe communication, which basically means it's almost real-time relay, in the sense that as soon as the data goes from the rover, making its way down through the Martian atmosphere, it's sending its signals to the Mars Reconnaissance Orbiter, and the Mars Reconnaissance Orbiter is just acting like a pipe that kind of bends that signal and sends it back to the Deep Space Network dishes on Earth. So that is the bent pipe that everyone's so excited about, and that's actually really important for getting the last 2 minutes of this landing event.
So we're all hopeful that as soon as it touches down, the cameras will record something. So check this out, you guys. When the thing, it's just like science fiction, except it's real. So when the thing comes down, it's, except it's on Mars, it'll sound different. And it'll kick up dust, just like, I don't know if you've ever been around a helicopter when it lands. It kicks up dust. All right. So the cameras have covers on them, just a lens cap, but the lens caps are clear. The camera can see right through its lens cap. So we're hoping it'll take we'll get a couple pictures right away, and then poink, or the lens caps will come off, and we'll get an even sharper, better picture. So Raquel, what do we do with ground penetrating radar now that it's there?
Yeah, no, this is really exciting. So the ground penetrating radar is going to help us understand the geological context of Jezreel crater. So we're going to be able to hopefully understand the different layers that are underneath it, so that we can pick really great sites to do some sample return. So doing some sampling of the rocks. And if we know the different layers underneath, that's really important. So essentially the ground penetrating radar sends out a signal out, and then we listen to the echoes. So depending on the different layers, the echoes come back at different times. So it gives us a picture of what the rover is driving on, of underneath the ground of where the rover is on.
So you guys, one of my favorite hilarious jokes that I find funny and other people look at me cross-eyed is, I start by saying, some of my best friends are geologists. When you talk to geologists, they're extraordinary. They think, Bethany, you can talk about this. If you have the right rock, you know who was president or something. Like, every rock tells a story, but the geologists get pretty carried away. You can tell who's going to be president. No, I exaggerate, but this whole thing that people have talked about since I joined the Planetary Society in 1980, when Carl Sagan and Bruce Murray and Lou Friedman started it, people wanted to bring rocks back from Mars because every rock tells a story. And so just think, everybody, if we could bring rocks back from Mars that have evidence of fossilized Martian Marscrobes, be extraordinary. So, Bethany, how are they going to do that?
Well, I'll go, and then Derek, I think was gonna jump in with a thought here. But I'll just, one of my Caltech colleagues sort of famously said, in terms of talking about sample return from planetary bodies, give me a single rock and I will tell you the history of that planet. Yeah. We may need more than just one rock, but the bottom line that's so exciting about this mission is it's really the culmination of something that planetary scientists have wanted to do for 50 years, which as soon as we realize the rich geologic record that Mars holds, including of the very earliest part of the evolution of planets at the beginnings of the solar system. I mean, this record is gone on Earth, but it is there at the surface of Mars to grab and bring back a sample. So it's incredibly exciting. I don't know, are you excited, Derek?
I am excited. The thing that I was actually thinking about was how Bill was talking about the sound of this craft moving through the Martian atmosphere and what that would sound like. And what that made me think of was that this mission has a microphone on board, which is something that the Planetary Society has been, lobbying for a long time. Is this going to be the first microphone that is actually active on the surface?
I believe the answer to that is yes. Someone can call in, fact check.
Yeah. But there's one on the surface, as we like to hilariously joke. And I was at a Planet Fest, Planetary Society event in 1999 with everybody's buddy, Buzz Aldrin. And the thing crashed. The Mars Climate Orbiter is on the south pole of Mars. Mars Polar Lander, I misspoke, is on the south pole of Mars, and so is the microphone, we presume, but it's in a rubble pile. But this time, we're pretty sure we're going to get a couple microphones there. And you guys, just to go on and on, I've been in meetings where people, I'm not going to say who, people said, well, you don't need to send a microphone to Mars. We know the composition of the Martian atmosphere. We know the atmospheric pressure of Mars. We know exactly what it's going to sound like. You don't need to send a microphone. But as the mythic test pilot, Tex Johnston, is supposed to have said, he did a barrel roll with a 707. On an airliner, he did a roll, did two of them. He said, one test is worth 1,000 expert opinions. And that is a worthy sentiment, my friends. We don't know exactly what it will sound like, and I am very excited. Now, how often, Bethany, do dust devils go by on Mars?
Dust devils are actually pretty darn frequent. So one of the things I'm privileged to also work on the Curiosity mission, and almost every day we take a dust devil movie, which basically means that we run one of the cameras so that it takes an image every few seconds, or most of them are tens of seconds, just snap, 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 images of the horizon. And, I don't know the exact statistics, but we catch an awful lot of dust devils, like hundreds per year. So they're a pretty common event, actually, a fun Martian weather phenomenon.
I want to hear what they sound like. That's what what does a Martian dust devil sound like? Yeah. Have you all, has anybody been through a tornado?
I have not, but my understanding would be that these dust devils would be much less violent. Like if you watch the movie The Martian, you wouldn't get that sort of force because of just how thin the atmosphere is. Is that
there's
right,
so few molecules per cubic, whatever the heck, meter. Yeah.
Yeah, that's one. It's one of the liberties of the Martian is, he probably wouldn't have been impaled by this. It's hard to get a lot of force from wind when your atmosphere is very, very thin. But hey, had to strand them somehow. And I really look forward to seeing what Mars hears, what Mars sounds like. We kind of got a hint of this from the InSight lander. I don't know if any of you Google InSight wind sound. One of the sensors picked up vibrations of the wind, so we have a bit of a sense of what it might sound like. But these will be the first true microphones on 2020.
It's just cool, you guys. So when I worked briefly on Spirit and Opportunity. Gee whiz, more than 15 years ago. The saying was, you want the cameras as high as a 10-year-old's eye. You want to have the experience of somebody being there, somebody being on the surface and feeling it, because you will just know. This is what we talk about humans all the time. You're going to notice something that it's hard to write software to notice. By having these sorts of observations, we're going to have insights, I guess that's a pun, about what goes on the surface of Mars. I mean, just think how hard it is, really, to get an image of, let's say, a water spout, a small, relatively small, spinning storm system at sea. It's difficult. We get images of them because there's so many cell phone cameras now, but just think if you landed on Earth one place in an area the size of a living room or what have you, how likely would it be that you'd see a dust devil or a water spout or a tornado? It'd be pretty hard, pretty unlikely, but these things happen so frequently on Mars. We have, I guess, would you say, thousands of pictures of them?
Yeah, that's right.
It's amazing. So, Derek, when you were talking with the people about the amazing helicopter,
yes,
what's the idea there? How is it going to work?
Well, it's a technology demonstration, right? So they're not going to try anything too ambitious in terms of science. They told me, the key is just to prove that you can fly on another planet, because that's a pretty daunting challenge in itself. And that the first flight is probably going to be a little hop up where it just, lifts up off the ground and there's a mutual selfie. So the helicopter takes a picture of the rover and the rover takes a picture of the helicopter, and then they're just going to sit back down. So I think if all is running well.
Though? Come on. How cool is that?
I mean, if they pull that off, it's just, to me, it's phenomenal, right? Because you can't drive this thing with the time delay. So it's got to fly itself. It's got to charge up these batteries, which are kind of equivalent to like 3 cell phones worth of battery. The thing weighs, at least on Earth, about as much as a laptop. So super light with these couple big rotors. And it's just going to try to get up in the air. And if things start going well, I think they're going to get more adventurous. And they can fly for up to 90 seconds. So, on Earth, that might not seem like a lot for a drone flight, but I feel like for flying a craft on a planet that far away on a different world autonomously, that sounds like forever. And if they're able to do a few of these hops, like, it's just going to be really opening up a new dimension to space exploration, because we've always been sort of limited to either orbiting or crawling along the ground. Now you've got this great ability maybe to go really fast and at a nice height above the surface to get lots of information very rapidly. So I think it's just incredible, super exciting.
Well, so the geologists always say they want mobility, like Raquel. When you find a layer with the radar, you want to go where it is. You want to be able to get to it. So this is a big thing Matt Dallenbach and those guys talk about all the time, is being able to see a rock and go to it. Well, with a helicopter, it just seems to me you can get to a lot cooler rock a lot faster. I mean, just cool.
Yeah, in geology, context is everything. You want to see, the extent of a geologic unit to try to understand, how it formed, how it has evolved over time, so that it would be hard, because the rover does drive pretty slowly. So if you have, maybe in future missions, if you have a bunch of, like, a swarm of these drones to fly around, you can get a much better picture of what your environment is. And I think that what's really great about this tech demo is that in the future, maybe we can have much more of these drones flying around, these helicopters flying around, both to get imagery, but maybe potentially they could help move things around in the future once humans get there. So yeah, I'm really excited to see what this helicopter does.
Let's go.
The things we're at JPL with the helicopters actually is, okay, we're like going to get the data back from the Ingenuity helicopter from Mars, process that, figure out what worked well, what didn't. But what we're already trying to figure out how to put larger payloads, like, what is a payload? That's the instruments, the stuff that scientists use to make measurements. So Ingenuity has a very small camera. But imagine that if we can hop from spot to spot and not just get images, but get, like, chemistry, like the things that we're using to look for life on Mars and look at minerals that record climate. So imagine if we could just fly around for miles and miles on Mars, hopping from spot to spot, recharging, maybe making chemical measurements at night, sitting in the morning to let our solar panels recharge, and moving to a new vista every day. That would be amazing. So this Ingenuity helicopter is sort of the first step of what we hope is that future.
It's just so ambitious, you guys. And, at the Planetary Society, I like to say we do at least three things. We educate, we have things like this. And these are shorthand expressions. We have a fabulous website. We host things like this in Planet Fest last weekend and this landing party today. We innovate, we have a LightSail 2 spacecraft. There's an image of the Nile River taken by LightSail 2. And in orbit right now, or on orbit right now. And that was built by contributions from the 50,000 of you around the world who just thought it was cool. And the estimates are we did it for about a 20th of what it would cost a regular space agency or administration to do. And the third thing we do is advocate. We go to European Space Agency, Canadian Space Agency, Japanese Aerospace Exploration Agency, Australian Space Agency, and the US NASA to advocate for space missions, for planetary science missions. Because you guys, people perceive the NASA budget, people think it's 10% of the federal budget. No, it's less than 0.5% of the federal budget. And the planetary science component or line item is 9% of that. It's 9% of 0.4%. It's a very, very small fraction of our tax dollars that go to these missions. And everywhere you are in the US and many, many places you are in the world, NASA affects your local economy. Money is being spent in your local economy in almost every county in the US. As the saying goes, money spent in space is actually money spent on Earth. And if we could make these discoveries that I've alluded to and Bethany and everybody have talked about, it would just be something else, you guys. It would just be profound. Evidence of life on another world. Hey, you like to think about things? Here's a couple things. First of all, Mars is smaller than the Earth, cooled off 1 billion years before the Earth did, had an ocean 1 billion years before the Earth did. Did life start on Mars? Mars is littered, covered, nailed with almost countless asteroid impacts. Did Mars get hit with an impactor? Stuff went through space, woo, 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 or as I like to say, and landed on Earth, and you and I are descendants of Martians. That is extraordinary, but it's not crazy. It's not absolutely nuts. It's something worth investigating. Then the other thing is just think how much we have learned about climate change by studying Venus and Mars. You know, in the 1980s, Jim Hansen and these guys realized that the Venusian atmosphere makes Venus crazy hot. And the Martian atmosphere keeps just warm enough to have ice and slush on Martian summer days. It's really an amazing thing. With a small investment, we seek answers to these amazing problems. All right. Whew. How are we doing out there? There's and there are the peanuts.
They brought up the lucky peanuts.
Yeah.
Ranger number 7, on the 7th attempt, decided to bring peanuts to the ops area just before the launch, and guess what? That mission worked. Now, we're not supposed to be too superstitious. We're engineers and scientists after all, but we love tradition. And ever since then, before launch and before critical events like entry, descent, landing, we have brought out peanuts and shared them with the team. And it's been really a wonderful little experience. And so this is something we will do. We're doing right now. And it's something that we just can't help ourselves. It's just part of the experience.
Well, speaking of the experience, how did the Perseverance team keep the tradition alive this year?
Well, this year we're passed out little packets of peanuts to the team, and they can sneak one peanut in their mouth as part of to keep the tradition alive. But you know, this is part of the COVID experience, but we can't leave this one undone. So this is what we're doing, and this is going to help us land safely.
All right, thanks, Rob. I have some questions for you a little later on, but we're heading back to Swati Mohan, who is part of the landing team. She'll be calling out key milestone and events as they happen from Mission Control. So let's listen in right now.
So right now we're still about 20 minutes from entry, and the EL phase is giving a last-minute confirmation of what will be happening in the upcoming changes to the vehicle, just to remind the team.
This will allow us to steer our trajectory as we make our way through the atmosphere. This is one of the things that allowed MSL, the Curiosity rover, to land where it did. And we're depending on the same type of entry guidance this time around to help get us very close to our target. As we make our way through entry, finish our guided entry profile, we'll do a maneuver called heading alignment, where we point toward the target and get ready to deploy the parachute. But before we deploy the parachute, we need to get rid of a set of balanced masses that have been giving us a center of gravity, or CG offset, throughout the guided entry phase. So these are called the entry balance masses. We also call this maneuver SUFR, S-U-F-R, or straighten up and fly right. So we'll go ahead and eject those masses when we get a trigger from the GNC system telling us that we're at the appropriate range to the target to do so. As soon as we deploy those...
How cool is this, you guys? Have these masses, we're going to let them go. And that'll straighten the space. It's just, wow. It's physics, people. That's physics. So, Derek, Raquel, you guys have a Tesla, right?
We do, yeah. How is this related?
Is it self-driving?
To a degree. I was driving in it last night very late, and I was relying on it pretty heavily to keep me going straight, flying right.
Because would you let go of the wheel for 7 minutes? Really?
Not 7 minutes, and you couldn't, because the thing would shut off. It tells you have to touch the wheel.
Yeah. But these guys, sure, we're going to Mars. It'll be fine. Yeah, just let go.
Let go and let the thousands of lines of code that have been triple, quadruple, quintuple checked against all possible scenarios. Let that take the wheel.
Yeah, and I remember very well the cold, what might affect the software that was tested and tested. Oh, here's Rob Manning. This guy, I've spent time with him. He is something else. Rob.
There's another radio that will continue transmitting a tone, so that like a flashlight that will allow us to at least see that the vehicle is still on, and that color of that flashlight tells us a little bit what state the rover's in. But soon after that, it won't be very long before we'll be able to hear more ones and zeros coming from the spacecraft. So this is a really exciting time, and it's just important to remind people this is there's a lot that can go wrong in a day like today. There are thousands of things that have to go right.
Yeah, we had success in the past landing on Mars. You'd think it gets easier, but it really doesn't. Why is it still so difficult?
Well, it's because it's involved thousands and thousands of things, hundreds of thousands of lines of code. There's 79 pyrotechnic devices. Each have to work perfectly. One critical wire short or one key thing mechanism that doesn't work or breaks, and it's mission over. And so it's and it's very easy. We're human beings. We're not perfect. Mistakes can be made. We count on each other to find our own mistakes, and we work very hard to learn from the mistakes of the past. We've had many failures. Remind people, roughly half, around half of the missions to Mars over history have failed. And so that could happen today too. Even though we've had a nice, wonderful string of successes in the United States, it's still still a bit of a gamble that we have hoped that we have erred in the side of luck, and we've stacked the deck and loaded the dice to make this thing succeed. But if we do fail, and if something bad happens today, I can tell you we're going to learn it. We'll have the data that tell us what happened. We'll know why. We'll figure it out, and if we are allowed, we will pick ourselves up and get us back on the horse. And if Congress and NASA allow, we will try again. As we always do, we will learn from our mistakes.
And what are the possible scenarios we could be looking at today?
Well, there's things like one of the key stressful elements for all of us is parachute inflation. But just even separating from the cruise stage is a pretty major event. Lots of devices have to work properly. Certainly, the heat shield separation, getting the descent engine started. There's no less than 16 rocket motors that have to work. 8 to control during entry, another 8 to control it during landing. I said it's a lot of stuff, and it all has to work. And guess what? We haven't done this before with this vehicle ever. This is its first attempt to actually land. We can't try this on Earth. We can't we don't have test pilots to try it out on this planet before the big show. So this vehicle is doing it for the first time. We've done the best testing we could do in bits and pieces, but it's as best as we could do. But I think our team is up to it. This team is the best. It's a diverse, intelligent, amazing group of people. People from all over the world who worked on this, not just here in California, but all over NASA, contributors from aerospace, universities, countries around the world. It is just an incredible, remarkable engineering achievement, and I am just so proud of this team.
Thanks, Rob. Now, let's listen back into mission control.
Right, we're about 14 minutes from entry interface. The vehicle is currently preparing the heat rejection system that has kept the thermal system cool inside the air shell for about the last 6 months. This will allow the spacecraft to more easily cut the line in upcoming cruise stage separation, which is under 4 minutes now.
Wow, 4 minutes, people. Whew.
Yeah, and that's when this
I was like that arrow on the side of luck too.
attached and ceiling the whole way comes off.
You guys,
It's just
if you're out there watching, would you please be nervous? Understand what's going on. They're on another world, and you can get into the science fiction thing. Well, it's already happened on Mars. Well, because of the speed of light, does it not happen here until that information gets here? Like, whoa, dude. The whole thing is just gives you such, to me, it's just inspirational that humans, that we could figure out how to do this is really amazing. It's worthy of respect.
I know it's just a robot. It kind of feels like it's me going to space. It's all of humanity. It's all of
yes,
there.
Yes. Testify. So we're less than 2 minutes?
I think we're about 2 minutes away from the cruise stage separation. Yeah. So what'll happen is the cruise stage separates, and then there's about 10 minutes before the descent stage enters the atmosphere. But the cruise stage separation is a big deal because these have been wedded together ever since they launched here on Earth, and we've got to have a successful separation to continue forward with the landing sequence.
It's all built into the software. We've tested it over and over and over again. This team has spent 24 hours a day, 7 days a week testing this thing for years. And so this is really the culmination of all that work. So this vehicle is getting ready to push that cruise stage away. Once it gets pushed away, the entry system with the rover inside, with the rover is still in charge, is going to get ready to take the vehicle, turn it to the right orientation, and aim it to Mars, and prepare for entering the atmosphere. This won't be long. Be prepared for this event.
We're about a minute and a half from cruise stage separation, about 11 minutes, 20 seconds from entry interface.
Okay, so it's about 10 minutes from cruise stage separation till entering the top of the atmosphere. From then on and out, things happen
We are
fast.
switching to MFSK tones. Telemetry will have stopped.
Telecom is confirming that the spacecraft has switched to broadcasting tones. These tones are received directly from Perseverance, but have very limited information content. We won't receive real-time information until about 9-10 minutes from now, once the Mars Reconnaissance Orbiter starts relaying information from Perseverance. We are under a minute from cruise stage separation, about 10.5 minutes from entry interface.
It's getting exciting. I have to admit, I am quite anxious, but very hopeful that this machine is going to do what we asked it to do.
We are seeing the heartbeat tones.
Okay, that means that there's no more ones and zeros coming. It's just the vehicle telling us it's still alive.
So, depends who you are. It's, Rob Manning's worked on this 20-some years, 30 years. And here's this moment.
For cruise stage separation.
That's
We
what
have
we believe
indication that
just
cruise
happened.
stage separation has been confirmed by the spacecraft.
We're off on a good start.
Congrats,
In
Bethany.
about 1 minute, Perseverance's landing software will wake up and begin the final preparations for entry. The first action it will do is to fire warm-up pulses with its entry thrusters. These pulses ensure that the spacecraft gets the thrust that it wants during entry interface. We're about 9 minutes from entry interface.
Okay, cruise stage away, warming up those engines that are going to have to turn on after having been off for 7-8 months since launch. So warming them back up again to get them ready to go.
After, when you're in deep space, it's 3
back.
Kelvin. It's almost absolute zero in deep space for 7 months. 7 months, I mean. Wow. and everybody, if you're watching this, we have closed caption in Spanish, Hindi, Arabic, Mandarin, we are gauging people around the world. It's very cool. This is a human endeavor, bringing out, I say all the time, bringing out the best in all of us.
The data stream indicating the crew stage separation. We have confirmation that the vehicle has started warming up those entry thrusters. Warm-up pulses have begun. At this point, the spacecraft is trying to stop its spin from the cruise 2 revolutions per minute down to 0, and then will turn to its desired orientation from entry. It will separate the 2 balance masses that has kept it balanced during all of cruise. This will allow the entry capsule to have lift when it enters the atmosphere. We have confirmation that the spacecraft has turned to the desired entry attitude. We are about 7.5 minutes from entry interface.
So, Bethany, right now we're going about 5 kilometers a second. We're going 10,000 miles an hour, something like that.
Yeah, you're doing a 5K. It's doing a 5K every second.
Every second.
Revolutions per minute.
And so it has that shape. Space capsules have that shape for the air, the aerodynamics, even on Mars, or maybe most especially on Mars, the aerodynamics.
Orientation and attitude via rockets on the back of that back shell.
Points carrier lock. The DTE from Radio Science from Green Bank reports carrier lock. You see the carrier on the downlink.
All right, that means the Green Bank telescope is listening successfully, locked on to the spacecraft.
We are continuing to wait for entry interface. We're about 6 minutes and 45 seconds from entry interface. We have confirmation from Greenback that they are receiving direct-to-Earth telemetry via that path. The spacecraft Perseverance is currently transmitting heartbeat tones. These tones indicate that Perseverance is operating normally and has nothing significant to report. This is as
nothing significant to report. We're just going into Mars at 10,000 miles an hour, but you know, it's routine. Nothing significant.
While we're in a quiet period, just a little preview. Once it hits the 6-minute countdown, that's when atmospheric entry happens. And then a whole bunch of steps happen real quick for about 7 minutes in terms of capsule going into guided entry, parachute up, heat shield off, rockets firing, parachute cut, descent, sky crane. It all happens super quick as soon as it hits the top of the atmosphere in this 6 minutes. And we'll just listen to them, I think, during that last bit.
We're still receiving heartbeat tones. We expect to continue receiving heartbeat tones until about 5 minutes after entry. At that time, Perseverance will be no longer in view of our antennas here on Earth. About 90 seconds prior to entry, the Mars Reconnaissance Orbiter should begin receiving telemetry from Perseverance and streaming it to Earth in near real time. There are a few expected short outages, such as when we have a plasma blackout or when we enter the peak heating phase. Aside from these outages caused by the plasma blackout, antenna switching, or high dynamic events, spacecraft events, we should have telemetry until about 90 seconds after landing. A plasma blackout is when the signal from Perseverance isn't strong enough to make it through the superheated, super fast air flowing around the spacecraft all the way down to Earth. Once the temperature drops below that peak heating, we do reacquire the signal from Perseverance. We are currently about 4.5 minutes from entry interface. Perseverance continues to report heartbeat tones, indicating everything is nominal.
Okay, what we're looking for now is Mars Reconnaissance Orbiter should be in view soon of our vehicle and be able to listen to ones and zeros coming from a separate radio that's really designed to talk between spacecraft.
MRO reports the electro radio is powered on, ready to receive signals from the lander.
Okay, MRO is ready and able and waiting for to hear from our rover.
Mars Reconnaissance Orbiter has reported that it's ready to receive the signals from Perseverance. It should be in a few minutes here. We're just
Flight Local 1
from entry interface.
Can you hear the way she breathes through her mask? Like she's put, whatever, at least 10 years into this thing. Here we go.
Health and well-being today to keep our nerves under control. But
around this time, a second spacecraft, MAVEN, should begin picking up telemetry from Perseverance and will continue to record that telemetry until several minutes post-landing. We won't get that data for several hours after landing as it's being recorded and then will be forwarded to Earth later. We are continuing to receive heartbeat tones, indicating that everything is nominal. We're currently at about 3 minutes until entry interface.
Okay. Very soon we'll be getting ones and zeros, I hope, from our radio on the rover. The entry interface is nothing more than just an arbitrary place in the sky that we've defined to be above the atmosphere. But from that point on, there's definitely atmosphere, and above it there isn't.
We are 2 minutes from entry interface. Perseverance is to transmit heartbeat tones, indicating everything is nominal.
It's like the Kármán limit in the Earth's atmosphere. Like it is, we'll just pick a spot. Okay, this is it. This is the atmosphere.
Well.
Yeah, and on Mars it's about 100 kilometers above the surface. So that's, kind of 12 Mount Everests stacked on top of each other is where we define that atmospheric entry point.
That's where you start experiencing drag, right? You start having to steer with the air, Martian air.
Yeah, that's one of the things that makes it so difficult to land on Mars. So Mars's atmosphere is thin enough to cause problems in terms of friction and heating, but it's too thin to be useful in terms of slowing the vehicle down appreciably. So that's what makes Mars so hard. It's a lot easier actually to land on the moon or an airless body than this super thin atmosphere. It's easier to land on Earth too with our thick atmosphere because you can use it to slow yourself down, but Mars is hard because it's this in between.
Yeah, landing on the moon's easy. Am I right, people? Yeah, it's nothing.
Easier.
Okay, that to me is it. It should be right now. Maybe 2 seconds from now. Oh, there we go.
After atmospheric entry, I think the next main event is a little bit after 12:49, 12:50, where we'll hit something called peak deceleration.
We're about 30 seconds from entry interface. Perseverance is going about 5.2 kilometers per second and is about 190 kilometers altitude above the surface of Mars.
Confirm your
It's like max Q on Earth, right? Maximum dynamic pressure when a rocket's sick. You got it. That's what you got to design for. God, I hope you guys thought of that.
From entry interface. 5.3 kilometers per second and an altitude of about 150 kilometers from the surface of Mars.
Can you imagine?
Just feel an atmosphere.
When you look at the Earth from space, that's about what you're seeing, Wow.
We have confirmation of entry interface. Perseverance is currently going 5.3 kilometers per second at an altitude of about 120 kilometers from the surface of Mars. The
right about now, it's
is now waiting until it begins feeling the atmosphere of Mars slow it down. Once there is enough atmosphere, it will start controlling its path to the landing target. Navigation is also confirming that we can see a little bit of that slowdown of the atmosphere on the Perseverance entry capsule. Our current velocity is about 5.36 kilometers per second and an altitude of about 67 kilometers from the surface.
We are probably seeing MRO plasma blackout at this point.
The vehicle should be doing its turns right now.
MRO has lost lock.
Perseverance. We have indications that Perseverance is now performing bank reversals in the atmosphere. These are the steps in order to control its distance to the landing target. Perseverance has just passed through the point of maximum deceleration and has indicated that it felt approximately 10 Earth Gs of deceleration.
MRO has lock again.
Yes.
10 Gs will make your eyes water, people.
10 Gs will make you faint.
Yeah.
From Mars Reconnaissance Orbiter during that peak heating phase, likely caused by the plasma blackout. Perseverance is still continuing to perform bank reversals in the atmosphere to control its distance to the landing target.
That means it's basically changing the angle at which it's going through. It's kind of tilting up a little to catch more atmosphere and adjusting accordingly. In about a minute, the parachute's going to come out, which is going to be...
Perseverance is going about 1 kilometers per second at an altitude of about 16 kilometers from the surface of Mars. We have entered heading alignment, which means Perseverance is no longer trying to control the distance to Mars, to the target on Mars, but instead is flying straight to the target.
Humans at their best, people. This is cool.
Our current velocity is about 550 meters per second at an altitude of about 15 kilometers from the surface.
5 soccer fields a second.
MRO's reporting good telemetry log.
We are coming upon the straighten up. We are starting the straighten up and fly right maneuver, where the spacecraft will jettison the entry balance masses in preparation for parachute deploy and to roll over to give the radar a better look at the ground.
Yes.
The navigation has confirmed that the parachute has deployed, and we are seeing significant deceleration in the velocity. Our current velocity is 440 meters per second at an altitude of about 12 kilometers from the surface of Mars.
That's right where it's supposed to be.
Perseverance is now slowed to subsonic speeds, and the heat shield has been separated. This allows both the radar and the cameras to get their first look at the surface. Current velocity is 145 meters per second at an altitude of about 9.5 kilometers above the surface.
So just 1 soccer field a second now. Football field.
Now the radar's ranging, looking for the ground.
It's down there.
Yes.
Perseverance now has radar lock on the ground. Current velocity is about 100 meters per second, 6.6 kilometers above the surface of Mars. Perseverance is continuing to descend on the parachute. We are coming up on the initialization of terrain relative navigation and subsequently the priming of the landing engines. Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
God, listen to her breathing.
We have confirmation that the lander vision system has produced a valid solution and part of terrain relative navigation. We have priming of the landing engine.
Description of they got a plan.
Taking
it has
photos.
a way to
It's
go.
doing photo matching, trying to find where it is and pick the safest spot.
About 2.6 kilometers from the surface of Mars. We have confirmation that the back shell has separated. We are currently performing the divert maneuver. Current velocity is about 75 meters per second at an altitude of about 1 kilometer off the surface of Mars.
TRN Safety Bravo.
We have completed our terrain relative navigation. Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars.
Gosh. You could, if you were there, you could make out a baseball on the surface.
Accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver.
We've lost direct to Earth tones.
That's expected.
As expected.
Sky crane maneuver has started. About 20 meters off the surface.
20 meters. It's right there. So close.
We're getting signals from MRO.
Signal from reconnaissance orbiter. The big pipe.
Touchdown confirmed. Perseverance safely on the surface of Mars. Ready to begin seeking the sands of past life. At this point, the descent stage has flown away to safe distance. Perseverance is continuing to transmit direct through Mars Reconnaissance Orbiter to Earth.
Wow, you guys, that was something else. I mean, we act like, of course, it was going to happen, but they really pulled it off. So let's see if we get these images. That's what's crazy making, man. It's just
Should be a couple few minutes.
When I go through that, the thing that I just keep thinking about is like the sophisticated orchestration of how that is possible, how that like requires the greatest of our intellect to, make that happen, not to mention a ton of money and a ton of time. I just feel like it's levels above most of the human achievements we normally see, which are always impressive. But this for me is like, the pinnacle.
It really is. It's so difficult. And, it's not just technically, it's not only technically difficult, but it's an organization. It's a management. It's how are we going to approach the problem? How are we going to coordinate all these world's foremost authorities to work together to achieve these things? And I know, Bethany, you were involved in these meetings, like, where are we going to land? Like that right there is just not a trivial choice, right? Where are we, by the way? Let's see. Here's a globe of Mars.
Go to the west side of the Isidis Basin, and just a little above the equator.
I found it the other day. You directed me there the other day. Okay, here's Planitia, Chrysa Planitia.
What about Utopia Planitia? Do you want me to grab my big globe, Bill? It's behind my shoulder.
Well, if you got time, yeah. While everybody's freaking out, that are very happy.
Perseverance is alive on the surface of Mars.
Here we go.
Congratulations to the mission. And looks like we have some more news in. It looks like we're getting the first image. Here, take
oh my
a look
God!
at the
Really?
image.
I'm stretching it for all of you.
Flight, this is OL3. I have the target point on the map when you are ready. We are ready, OL3. Go for it.
Wow. Where are we? Where are we?
All right. We'll take it. We'll take it.
Flight, I'll be moving in, showing you the safe zone that we've landed in.
Here's a picture.
The team has just put the first image from Perseverance on the surface of Mars. Now, it comes from the engineering cameras, known as the hazard camera. This camera is mainly used to help the rover drive safely around Mars, and we will get higher resolution photos later in the day.
Later in the day. Like
Yeah.
right now. It's just,
You want it all right
gee.
now.
So this is something that always wigs me out about these images from Mars is it's a place. You know, if you were somehow dressed properly, the right spacesuit, Sandy the squirrel helmet, you could walk around, you know, have a picnic carefully. But it's a place with rocks and sand and history and geologic information locked in the rocks, and it's really amazing, you all. It's amazing. I am honored to be a human today. It's not bad.
Yeah, it's a great view. Can't wait to get exploring. They were just trying to show, I don't know, we didn't get a good video feed. They're trying to show where we are, and it looks like the question is, did we land on the delta, or are we just to the side and we're going to be able to like turn around and stare at it? That's what I'm trying to figure out right now, is where exactly did we land? We clearly landed safely, but where are we? Hopefully they'll have a chance to get that up on the view for everyone.
Got our second image in. Our second image is in.
Okay, these we have a camera in the front and rear of the spacecraft. They're near the ground, so these are pretty close. So you can see the wheels there, and they're a little dirty because we've got glass covers over these cameras. But we took these seconds after landing, so there's still dust in the air from our landing event. So this is happening. This happened just seconds ago. Just arrived, and this is really amazing. And we even know where we landed. This is the most amazing thing. The vehicle has told us where it's landed because it figured it out. You know, this is a sign. NASA works. NASA works. And when we put our arms together and our hands together and our brains together, we can succeed. This is what NASA does. This is what we can do as a country on all of the problems we have. We need to work together to do these kinds of things and make success happen.
He said it. He said it. Bringing this team together to do this extraordinary technical feat requires bringing people together who are, oh, here she goes. Here she goes. Bring people together. Amazing.
Thank you. What an amazing day.
And how does it feel to have another rover on Mars?
It's amazing. To have Perseverance join Curiosity on Mars, and just a credit to the team. I mean, just what an amazing team to work through all the adversity that goes and all the challenges that go with landing a rover on Mars, plus the challenges of COVID, and just an amazing accomplishment.
And what does this mean for NASA and its future plans?
So for robotic exploration, every time we execute a mission with new instruments, we discover new things and things we never thought we would discover. So that always informs our future robotic missions, both landers, rovers, and orbiters. This mission also has technology on it. One of the cool things is the Ingenuity helicopter. It's an experiment on this mission. But if it's successful, we can use it as an science observation platform by putting instruments on it, and also use it as a scout for future rover missions. And then just the entry, descent, and landing capability. It'll allow us to land more larger, more ambitious robots on the surface of Mars. And then for human exploration, we have the Mars Entry, Descent, and Landing Instrumentation, which is going to give us EDL information. We have the Mars Environmental Dynamics Analyzer. It's going to give us size and properties of dust particles, because when we send people, we're going to have to deal with that dust. This is just an incredible mission because of the science and the technology, and then caching samples for a Mars sample return mission. That will be an amazing mission, the first round trip to Mars and back, and bringing those samples cached by Perseverance back to Earth to examine with state-of-the-art equipment in our laboratories here on Earth.
We have so much to look forward to. And we also have a student question coming in from Landon. Let's take a look.
Hi, my name is Landon Applegate. I'm in 6th grade and I'm going to Academy for Academic Excellence. And my question is, do you think we could get resources from Mars to help on future missions or even as like a launching point?
Great question, Landon. Actually, we have an experiment called the Mars Oxygen In Situ Resource Utilization Experiment, or MOXIE, and it's going to demonstrate generating oxygen from atmospheric CO2, and that could help generate breathable oxygen, and even if we can liquefy it, oxidizer for propulsion systems. So that's a tech demo on Perseverance. And then we're going to continue to characterize the frozen water on and below the surface of Mars, and eventually try to figure out how to extract that water from the Martian soil, or what we call regolith. And then we can use that for potable water and also break it down into oxygen and hydrogen for rocket fuel. So absolutely, we're going to try to eventually figure out how to live off the land to support human missions to Mars.
Thanks for taking the time to talk to us today, Steve.
Thank you.
And now that Perseverance has safely touched down on Mars, let's learn more about what's in store for the rover. Joining us now is Surface Mission Manager Jessica Samuels. Jessica, your surface operations team has now taken over. What are they doing now?
Yes, hi Raquel. We are so excited here in the Surface Mission Support area. The team will do a handover with the entry, descent, and landing team and pass any critical information. And then this team behind us will be the team that does the health and safety assessments daily as we progress on this mission.
And what do the upcoming weeks look like for your team?
Right. Exactly. One of the few interviews with that. Yeah, I mean, looking forward, it's just going to be an incredible few days. So even while we're celebrating and like high-fiving, fist bumping, whatever, here on Earth, Perseverance is still at work on Mars. All the orbiters are out of the field of view, so we're not actually talking to it right now. But what's happening is that what should be happening anyway is that the covers on these cameras are popping off. Another thing that's happening is there's sort of a switch of software because there was an entry, descent, and landing sort of mode that the rover was in. Now it is switching to surface mode in order that we're able to, start getting to work. So that's what's happening kind of over the next 4 or 5 hours. There's going to be another communications pass at about 4:30 Pacific, and then another one at 6:30 Pacific as we see the rover go through its transformation from interplanetary Voyager to Geologist Explorer.
So, we're just going to change software on another world. Yeah, that's what we do.
It's hard enough, right? When you're on your laptop here on Earth, imagine doing it on another planet.
Every time I upgrade, it's like, exactly we're going to work tomorrow? Say it again, Derek.
I was just saying, where exactly are we? Bethany, do you have that info?
Where are we?
Well, okay, let me get my big globe. One moment.
We'll be here.
All right, I'm going to get the big globe. And this big globe is like super color psychedelic Mars because blue is low and red is high. So you've like got the big volcanoes of Olympus Mons, and then, the big canyon of Valles Marineris. And if we keep rotating, still rotating, I have actually put an orange spot near where we are. So Jezreel crater. So we're on the edge of this large impact basin called the Isidis Basin. And Jezreel crater is right about here. And so all those beautiful images you see of that delta in that former crater lake, that's a 45-kilometer crater. You can't really see it super well on my big globe, but that's where we are. And it looks like, I'm not 100% sure because they didn't really flash it on the scene, but it looks like we didn't land on the delta itself. It looks like we landed on the crater floor, so that I was kind of wondering if in the background of one of those HazCam images, there was a little bit of a scarp of a delta front. I think it looked like, from what I was seeing on the images in the background, they were kind of at the floor. And so we'll be able to look up toward the delta. I hope they put those images on the feed or post them on the web.
Did you just toss out a geology word, a scarf? A scarp?
A scarp. Yeah, that's kind of like a cliff face.
And so this is what geologists and paleontologists go for. They want to see where Mother Nature has cut the scarp, so you can see. You don't have to do the digging or use your radar, Raquel.
That's exactly right. We can look underground with Raquel's radar. I just have to tell you, I have to share. I am just so, it's just kind of a moment because when I was in graduate school, my very first paper was about this location on Mars. So I pored over this particular spot for hours and hours. The first paper I published in graduate school was the finding of clay minerals in Jezreel crater. The second was about carbonates in Jezreel crater. And to think that image that, hours and hours in the lab poring over it, staring at it, we're now there. We're now actually there to be able to explore. So it's going to be amazing, y'all. This is a good spot.
It's a great spot right there.
In terms of like where we actually set down, if we didn't, set down on the delta, like you're saying, if we're like a little bit beside it, why would the craft have made that decision? Is that kind of like an autonomous decision that would be made, like based on, like, did it have programming to decide, okay, if I see something nice over here, I'm going to go there, or?
Yeah, basically. There was a pre-programmed hazard map on board. So you may have seen in the background this splotchy map of like reds and greens and blues. Those splotches were red is hazard, avoid it. Blues and greens are okay, aim for that. So if you heard them say terrain relative navigation, and one of the things that it was doing is during its controlled descent, it was trying to line itself up with one of those green-blue patches. So in terms of where exactly it landed within the ellipse, it kind of probably had to do how far down range it had gone before it got to the altitude where it needed to start looking for a safe spot. So I haven't seen, where it is in the bullseye of the ellipse. I look forward to, seeing that on the feed or on the web. But that's how it picked the spot. It was looking for one of those blue-green lily pads in its pre-programmed map.
So if you had your druthers as the landing person who picks the landing, do you want to be off to the side of the delta, or do you want to be right on the delta?
Both are great. We want to eventually visit all of the units. I'm super curious where we are. If I had my total complete druthers, I would want to have landed in the western part of the landing ellipse, because that means we can do the science of the crater floor, the science of the delta, and then get up out of the crater into even older units through the canyon that the river that fed into the crater carved. So we can go, up canyoning sooner. I am happy we are safe on Mars.
And we can drive around. We got plutonium. And we got new wheels, new tires, better tires than Curiosity, which were fine tires, but they wore out a little, right? They got a little worn out.
Something I'm always asked is like, how do we pick that place? I've been to a couple of the NASA of the landing site selection meetings, but people ask me that all the time. How do we end up deciding why Jezreel of all places, and how does that process work? And I've seen you, Bethany, at all of the meetings, so maybe we can talk a little bit about that. That'd be cool.
Yeah, sure. I mean, so the landing site process started, oh gosh, how long ago? Maybe it was 2014 or something like that, with several dozen sites. So basically, you can only land on Mars where it's safe to land. You can only land below about -2 kilometers elevation. But then beyond that, it was left open to the science community. Propose a site. Pitch it, right? So the first workshop was like the ultimate like pitch day, where there are 3 or 4 dozen landing sites and a quick rapid fire set of presentations. And by the end of the first 3-day workshop, that list had been narrowed down to about 12 or 15 that were then going to stay on the list and continue forward. And then they get vetted for safety. You want to make sure you can survive, so that chucks out some of them. But then, then you get down to there's 6 or 8 left, and they're all looking pretty good. They all have science pros and cons. Some of them are older, some of them are younger, some of them preserve lakes like Jezreel, some of them preserve hydrothermal environments, some of them preserve volcanoes. So I have to admit, Jezreel was I was co-proposer of Jezreel. I was also co-proposer of a site called Northeast Syrtis and Midway. I slightly preferred that second site, but what's amazing about Jezreel is that with Jezreel, you can do Jezreel science and then you can drive out and you can get the rest of the science too. So it's like the ultimate landing site, in my opinion, because you get the Paleo Lake and then you drive out and you get volcanic units, impact units, and ancient hydrothermal systems that are 4 billion years old. So with Jezreel, you get a 3 billion year old lake and then a 1 billion years more back in Martian time.
How old is Mars? Is like Earth, 4.5 billion years, right? Maybe 4.6 if you're counting.
You got it.
Rocks coming together. But you threw out a geology word there, units, right? A unit is an area, a volume of geologic of rocks of the same kind, huh? Homogeneous rocks.
Yeah. You want me
Is
to
that
take
right?
this, or Raquel to take this too?
Yeah, no, it's a unit. It's usually it was formed at the same time, so there's some continuity, and so we can learn about the environment that formed each unit by studying that unit, because it was formed in very specific environments in a specific time, and that's when you see different layers, we call those different units, geologic units.
Yeah, it's just you throw these words around like Paleo Lake, geologic units, what you got there, yeah. But it's a result of a lot of thinking, and you guys you try to imagine what 4 billion years is. I mean, a lot can go on in 4 billion years. You know? If you try to count to 1,000, takes you 20 minutes. You try to count to 1,000,000, staying up all night, not sipping a milkshake, that takes you 11 plus days. If you want to count to 1 billion, not sleeping at all, 1 a second, take you 31 years, 7 months. Okay. You want to count to 4 billion? You're getting into 130 years, 120 some years. Just counting every second. It's just really hard to imagine 1 billion years. And yet we can. We can imagine it. We can try to understand it. It's really amazing. The whole thing's amazing. So my understanding is they're off, the team is off looking for the next image. But man, landed on Mars. And Rob Manning pointed out, not only is it fuzzy, was the image a little grayed out or what have you, because there's dust on the lens cap, but there's still dust in the air after the rockets or whatever it sounds like on Mars. After that was done, then how long does it take you guys for dust to settle on Mars? Like, let's say on Earth, dust might take 10 minutes. If I blow up ash from the fireplace or off a book that's been on the shelf, it might take 10 minutes for dust to get to the floor or the bookshelf. How long does it take on Mars with the air so thin and the dust so fine?
This is a great physics problem for a high school class. Stokes settling.
Well, it involves aerodynamics. I mean,
depends on particle size and aerodynamics and the drag coefficient. And I have to admit, I cannot pull out those parameters for Mars off the top of my head.
Well, but having
Derek, you're a physicist, right? Aren't you a physicist? Can you pull that off the top of your head?
I don't have the calculation off the top of my head, but I would guess it's quicker. I know obviously on the moon it's much quicker, even though there's less gravity because you don't have that air resistance to worry about. So yeah, my suspicion would be it's a fair bit faster for dust to settle. But I don't know. What do you think? If the particulates are really small, like maybe it is a long.
Yeah, I mean it's a size function, right? So the big ones go first, then the little particulates, and then the finest of the fine.
Well,
I think it would
Doc,
be quicker.
Let me ask it of you all this way. How long was it before how long was it between the rockets blasting sand up or dust up, regolith up on Mars, and that picture coming down. That would give us a little delta, a time difference right there. It seems like, was it 10 minutes or a minute? So fun. It's so fun to think about this stuff because it means we're understanding. See, the premise of the bit, everybody, in science is that the universe is knowable, and the laws of physics we discover here on Earth must work the same on Mars. And if they don't, there's some other law of physics that we got to figure out. Over to you.
Yeah, I mean, that's truly the amazing part, right? And how can we land on Mars? Because we understand physics. Mars was where we expected it to be. So when we had a spacecraft there, we calculated the orbit, right? The drag of the atmosphere, the velocity through the atmosphere was what we expected it to be. We had a model that we could write out to predict it. The thrusters acted the way they acted, and so we have a new spacecraft on Mars. It's the power of the human mind, the power of scientific thought, and the power of engineering, right? Get it done. So I'm really excited about the future.
So, Derek, are you an engineer? Is your degree in engineering or a combined degree?
Engineering physics was my first degree, Bill. I don't know if you know about the engineer's ring. Can you see that?
Yeah,
it's a Canadian engineer.
Yeah.
Canadian engineer. Cool. Because I'm a mechanical engineer. I got a license. I got a number. Hey, wait a sec. Okay. I'm looking at the screen now that it's big. They've made me big. I mean, the screen big. So I just want to take a second. So here's a conventional globe of Mars. And here is, wait, I had it. Nobody leave this room. Yeah. Here's about where we landed on Mars. But, and then here is my fabulous MOVA globe, which you can do this with. And you guys, if you don't have a MOVA globe, I can't say enough good things. Light, sources of light make it spin. Light goes through the map, they call it, and then hits this little solar panel, and it reacts against the Earth's magnetic field. Big, stupid fun. It spins on your desk all day. Anyway, I hope many of you watching are members of the Planetary Society. That's why we're doing this. The world's largest independent space interest organization. And on the back of my business card, I have a picture of Mars, and there's the little instrument I worked on back in 2003. Anyway, check us out at planetary.org. And I mentioned this, I almost forgot, but the MOVA Globe Company is making you a deal. There it is. If you hook up now, you can get the Enceladus globe. Enceladus is a moon of Saturn that is also extraordinary, and we're sending a mission there in the coming decade. And one of our people on our advisory council, Deepak Srinivasan, is involved in this. Very cool. And if you call now, wait, there's more. You can buy any MOVA globe for 10% off. No, really, you guys. They are big fun. They're inspiring. They give you, they come in all different styles. So check it out. And of course, consider joining the Planetary Society. We go to U.S. Congress and other space agencies around the world to promote planetary science, because I like to say, although I applied to be an astronaut 4 times, you guys, I did. The planetary science is where we're making these amazing discoveries that just change the way we think about everything. And the exploration of Mars, as Carl Sagan said all the time, it's comparative planetology. It was a phrase he used often enough. You learn more about your own world when you study other worlds. And when you got globes on your desk, look at you guys, you've all got globes. Everybody's got globes back there. Yeah. You got a couple globes. Hey, Raquel, what is that behind you, that color-coded something or other?
So that's a geologic map of the moon's southern pole.
Well,
so the different colors.
I was just helping the other viewers understand it. I mean, so go on about that.
Yeah, so the different colors we were talking about, geologic units. So each color is a different geologic unit on the moon's southern pole.
And you guys are pretty sold on the idea there's ice there, right?
Yes. Yes, that's
100%.
right.
And Bethany, you got to go, right?
I'm like taking off the jacket that I, kept on to be the
Oh, wow.
formal president of Planetary Society, because now I'm just a member of the Mars 2020 team, just like the rest of them in the room. But I've actually got to go get to work and head to JPL. So I am so thrilled. It was a delight to share this with you, share this with everyone. If you like this, become a member of the Planetary Society, because we celebrate these moments together and we advocate for more of these moments so that they inspire the next generation. So thank you all. It's been a pleasure. Derek, Raquel, Bill, wonderful to share the moment with you.
It was just great, Bethany. You drive safely. And are you going to be living on Mars time?
We'll be living on Mars time for about 2-3 months. I'm going to be doing a hybrid myself. I got some day job things to take care of. But yeah, the team transitions to living like a Martian.
God, it's crazy. They get up 48 minutes later every day for 3 months. It's nutty. And my Jim Bell, who was on our board, and was your predecessor as president, he just said he opened an account at Starbucks. It was just a lot of, but you drive safely, pal. Thank you for taking the time today to share this moment with us. And while I'm looking over my shoulder, now that you've made my camera big, there's that image right there is the picture of Earth taken by LightSail 2, which the Planetary Society, you all paid for. And we have extraordinary people in that mission team, and it's still flying. It's flying at kind of an extra year because we figured out how to maneuver a solar sail in Earth orbit. First time it's ever been done. Well, anyway, we're winding down. Derek, Raquel, thank you so much. Oh, there's a button. They're telling me there's a button on the homepage to become a member, of course, of the Planetary Society. It's you guys, we just have a cool website, very informative. We have the best journalists in the world for planetary science. We support this mission. The microphone goes back to Planetary Society, advocating it back in, after the Viking landing. I mean, I've been advocating for it in a small way since 1980, which is quite a while. That was when disco gave way to punk rock, a very important time, maybe. But also, just notice that Viking landed in 1976. The next mission wasn't till Sojourner in 1997. And a lot of that was the work of the Planetary Society, going to congressmen, senators, congresswomen, and advocating for planetary missions. And our day of action is coming up. It's going to be virtual this year. Instead of going to the U.S. Congress, we had people come from Alaska and Hawaii last year to go to the U.S. Congress, advocate with your representative, your senator. We're going to do it virtually this year, but I'm pretty confident we're going to be all back together next year. By the way, everybody, I got my second shot yesterday, and I guess I had no side effects. I mean, except I'm very excited about Mars. I'm not sure that was a side effect. Raquel, Derek, thanks so much, man. Woman, it's just cool. And best of luck in school. How much longer are you in for, Raquel?
I defend in hopefully in September. So I'm almost done.
You'll be
really
done?
Excited.
Your thesis will be done?
Yes, hopefully.
Wow, congratulations. Here's to you. That's amazing. That is huge. Well, you guys are winding down. Derek, Raquel, do you want to, can you add some big final?
Mars Donuts. We've got Mars Donuts, I think Raquel organized upstairs. So I'm going to go sort that out.
There we go. Some Mars
and you
Donuts.
pre-ordered them, huh? So
I did, because they were sold out.
They're red with chocolate sprinkles representing the roughness, the asperity, the units, the geologic units. Wow. Wow. That's, as the kids say, some pretty good grubbing right there. And you guys, speaking of grubbing, you know, we do have experiments on this spacecraft to see if we can utilize resources in situ, in the situation. ISRU has been going on a long time. In situ resource utilization has been going back since the 1980s. This is one more step in understanding our place in the cosmos and what I like to call our place in space. All right, you guys. Thanks so much for taking the time. Thank you.
Thanks, Bill. It's been a pleasure.
It's that time of day here in the Pacific time zone. We got work to do on Mars. Thank you, everyone, for listening. Let's get out there, understand our place in space, and change the world for the better. Thank you.